Unit 2A, Lesson 5. This lesson will align with Lesson 9.6 in your textbooks. The one standard we're going to work with in this lesson: use trig ratios and the Pythagorean theorem to solve right triangles in applied problems. What it means to solve a right triangle is that in the end you're going to find all three angles and find all three side lengths. So when we're given the problem, we're going to know usually three pieces of information: a combination of some of the angles and some of the side lengths. Then we have to use that information and what we know about SOHCAHTOA and the Pythagorean theorem to find the missing pieces. In the first example, we want to use the given information to solve the right triangle. So we have the right triangle CDE. We know what the length of CD is, and we know what angle D is. Angle D is 60 degrees, and angle E is 90 degrees. So the three pieces of information we need to find: the measure of angle C, and the length of DE, and the length of CE. Well, since this is a right triangle, we know this is 90 degrees and 60 degrees, and all three angles added together must be 180. So 180 minus 90 is 90. 90 minus 60 is 30 degrees. So since we knew what one of the acute angles was to start away, it's really easy to find the other acute angle. Now we're going to use the idea of SOHCAHTOA to find some of the missing side lengths. I'm going to use angle D as my reference point. So the sine of 60 degrees. We know sine is equal to opposite over hypotenuse, so this will be CE over 4. So now if I want to get CE, that length, isolated by itself, I need to multiply both sides by 4. So we get CE is equal to, now you want to make sure if you're using your calculator that it's in degree mode, and if you type in 4 times the sine of 60 degrees, you get approximately 3.46. Normally we round to 2 decimal places, and I should not have an equal sign there. That should be approximately, because we rounded that to 2 decimal places. So I'm going to change that up here, approximately 3.46. Now we need to find the length of DE. Technically, we could use the Pythagorean theorem because we know what the hypotenuse and one of the legs are. It's best if we use a trig ratio because the value we have for this leg is an approximation. We already rounded, so it's not a best practice to use a rounded value. If we use a trig ratio, we're going to get a better approximation in the end. So if I take the sine of 30 degrees, the sine of 30 degrees opposite over hypotenuse, that'll be DE over 4. Same setup as the last part, multiply 4 to both sides. So now if we type that in on your calculators, you will get that DE is equal to 2. Okay, we get an exact value for that length. So now we have all three angles, all three side lengths. So we have solved this right triangle. Okay, we actually could have gotten an exact value for CE. That is something, make sure you ask me in class. We'll go through this. Because this is a 30, 60, 90 triangle, the side lengths have a special relationship. Example 2, we're going to use the given information to solve this right triangle. This one's slightly different because rather than knowing one of the acute angles, we don't know either of those, but we know both legs. So the first thing we're going to do in this example is find the length of the hypotenuse using the Pythagorean theorem. So a squared plus b squared is equal to c squared. So 3 radical 11 squared plus radical 33 squared is equal to c squared. So now if we square that, 3 squared is 9, radical 11 squared is 11. So 9 times 11 plus 33 is equal to c squared. 9 times 11 is 99. 99 plus 33 is 132 is equal to c squared. Then if we take the square root, we can break the square root of 132 down into the square root of 4 times the square root of 33, which will simplify to 2 radical 33. So we know the length of the hypotenuse is 2 radical, oh, that was not good, 2 radical 33. Now we're going to use a trig ratio in order to find one of the acute angles. So I'm going to use cosine of angle H, which will be equal to the adjacent over the hypotenuse, which is radical 33 over 2 radical 33, which would simplify down to 1 over 2. So we have the cosine of H is equal to 1/2. In order to get that angle by itself, we have to use an inverse trig function, which we haven't talked about yet. So I need to take the inverse cosine of each side of the equation. What I do to one side of the equation, I must do to the other side. So on the left side, I'm going to take the inverse cosine, which is just a cosine, and it looks like it's raised to the -1 power. That's not an exponent. That denotes that this is the inverse cosine function. So the inverse cosine of the cosine of H equal to the inverse cosine of 1/2. Alright? The reason we take the inverse cosine is that the inverse cosine and cosine cancel each other out. So we're left with H is equal to the inverse cosine of 1/2, which, if you use your calculators, type that in, make sure you're in degree mode, you will get that the value for the measure of angle H is equal to 60 degrees. So now that we know angle H is 60 degrees, since we have the right angle 90 plus 60 is 150, so 180 degrees minus 150, we know then that the measure of angle I must be 30 degrees. So when you're not given either of the two acute angles, you're going to have to use inverse trig functions in order to find one of the two missing acute angles. So now we know all three angles and all three side lengths, so we've solved this right triangle. Now we're going to go through a very important application problem. A 6-meter long ladder leans against a building. If the ladder makes an angle of 60 degrees with the ground, how far up the wall does the ladder reach? And then how far from the wall is the base of the ladder? Alright, so got a little drawing to the right, might not be drawn to scale. We know the length of the ladder is 6 meters long and makes an angle with the ground 60 degrees. So we want to find out how high up the side of the building is the ladder and how far away from the base of the building is the ladder. Okay, so two pieces of information we're going to find. First, let's solve for H. So if this is the angle we know, we need to find the opposite side, and we know the hypotenuse, so we need to use sine. Sine of 60 degrees is equal to H over 6. Then if we want to set up an equation to solve for B, if this is the angle we're using again, we need to find the adjacent side, and we know the hypotenuse, so we have to use cosine. So then the cosine of 60 degrees is equal to B over 6. In both these equations, all we're going to do is multiply both sides of the equation by 6. And we will get some approximations. So now if you just type those in on your calculators, so if you type in 6 times the sine of 60 degrees, you'll get approximately 5.196, which we can just round to 5.2 meters. So that's how far up the side of the building that's going to go. And then if you type in 6 times the cosine of 60 degrees, that is going to be equal to 3 meters. So that's how far from the base of the building the ladder is. So to quickly recap what we talked about in this lesson, you use trig ratios in order to solve right triangles, meaning you found all 3 side lengths and all 3 angles. You also use trig ratios to solve an application problem. Remember that if you're solving a right triangle where you don't know either of the 2 acute angles, you're going to have to use inverse trig functions in order to solve for one of the acute angles.